Right. So on Monday, we were talking about the ice skater effect, and that is the effect that happens when an ice skater is spinning with her or his arms out and then pulls them in and spins faster. So we've already explained how pulling your arms in leaves the angular momentum of the system unchanged. And so because the angular momentum is conserved, because there's no net torque, what we end up with is the moment of inertia going down, so the angular velocity goes up. So that explains why this happens. However, at the end of lecture on Monday, I was trying to explain that indeed, the kinetic energy of the system goes up. So the question is if the angular momentum is conserved, but the kinetic energy isn't, and in fact the kinetic energy increases, assuming there's no losses due to friction and so on and so forth, where does that extra energy come from? And so what I did is I took the final value of the angular velocity, omega sub f, that we solved for using angular momentum conservation, and I plugged that into the formula for moment of inertia, for rotational kinetic energy, where the moment of inertia is just this simplified picture where we have the ice skater with moment of inertia I, and the mass, which is just some point mass at distance r from the center of the ice skater. And so you can plug in the values to solve for the kinetic energy, for the initial and final kinetic energies. And we find that the change in kinetic energy is greater than 0, i.e. the kinetic energy goes up. And so what we said last time is that, well, the extra energy can't come from work done, or can't come from rotational work, right? Instead, it has to come, and the reason why it can't come from rotational work is because the torque is 0, the net torque is 0. And so rotational work is work done by net torque. So what instead we determined is that there is one force that we have not accounted for, which up until now was an external force. We did not account for the force that causes the mass to be pulled in, right? We didn't account for that. And so if we didn't account for that when computing our energies, then that means that we can treat that as an external work. Think of it as perhaps somebody pushing that in, that is external to the system. And the motion that you have to undergo in order to pull the weight away from far away to close is its motion in the direction, or in the radial direction. It's radially inwards. And so the force is radially inwards. So what we can do is we can actually compute the work explicitly, given the magnitude of the force, or the magnitude of the force, and we already know the path. The path is from out to in, so the radial direction from lowercase, or from say x equals capital R to x equals 0. Maybe this axis is plus x, for example, at least in this one instant. And the pulling force is in the inward direction. And so what we can do is we can just compute the work explicitly, assuming that assuming that the force is always inwards. We can just take this dot product and it will always be negative, this inner dot product here, because F pull is towards the center of is inward and dr is outward. And because we're integrating from capital R to 0, the integral of something that's always negative will be always positive. So we get that the work done by this external force, this pulling force inwards, is greater than 0, and that checks out because we know that the kinetic energy of our system is greater than 0. So by the work energy theorem, everything's fine. Now, I did this calculation explicitly, assuming a constant pulling force, but it doesn't have to be a constant pulling force. It could just as well just be a force that's changing in magnitude with time or with distance, as long as it's always in the same direction. This will work out. So I know that that's relatively complicated, especially because this inward pulling force is kind of changing with it, like, at least in principle, could be changing with time or with position. And then there's this extra factor of I. So what we can do instead is we can again simplify, which is what we do in physics a lot. We try to boil this problem down to its simplest essence. So a simpler example of this phenomenon is the following. Let's say that you have like a table or something like that. And in the table, you have a small hole. Let me draw this a little bit smaller. In the table, you have a small hole at the center. And through that hole is a string. And it comes out that hole, attaches to a mass, and that mass is initially a distance r sub I away. And that mass is spinning around in a circle on the table. Assume the table is frictionless with some speed omega sub I. And what we're going to do is we know that in order for the mass to keep spinning around, there has to be some inward pulling force. And so in order to get there to be an inward pulling force there, we can apply a tension downwards. So what we do is we pull here downwards in order to apply the appropriate force to keep it spinning. But then what we do is we pull just a little bit harder. So not only is there enough force to keep it going in a circular motion, now there's a little bit of extra force that's bringing it ever slowly inward. So what ends up happening is you still have circular motion because the force is only very slightly greater, and we don't want any radial component to the motion. But now we just have a slightly smaller circle. Let's draw it smaller. Maybe that circle has radius r sub f. So now we can actually try to figure out how much work is done when the distance from the block to the hole changes. Or, right, like this block is sliding around, and we can figure out how much work is done by pulling. So the first way that we can compute the work done, well, let me just jot down what we want first. We want to know the work done by the pulling force. So by the way, when we are pulling down, if we're just pulling down with precisely enough force to keep the object moving in a circle, there's no work done because the force is applied, but it's not applied over a distance. In order to have work to be done, you need to apply that force, and that force needs to be applied over some distance, which might be this distance here, for example. So the first method that we can use is just the integral method, just compute the integral of the work. So we need the pulling force to just barely exceed the tension force. And I'm going to call F tension that's the force that's needed to keep the object spinning in a circle. So imagine that initially there was some force F tension pulling downwards, and then we just add just a smidge extra force in the form of F pull, for example. And the reason we need this to happen is that otherwise the block will acquire a radial component to its velocity. And we don't want that. We want it to keep moving in a circle and not just start moving inwards. Perhaps a way to think about this is that imagine that there might be a friction force on the surface of this table, but that friction force is only applied in the radially outward direction. And perhaps there's only kinetic friction, so that you yank it in a little bit, and so for a brief moment it acquires a radial component to its velocity, but then the friction quickly kills that off. So all you've effectively done is you've just changed the radius of the circular orbit, but you haven't changed the shape of this orbit. So in that case, the work done from I to F, which is, initial here and final here, this is the integral from I to F of the pulling force dot dl, well, which is equal to r sub I to r sub F, which is equal to just the magnitude of the force. I'm just going to call that F. Come on, I can write better. F. And then the direction of the force is minus, say, let's say d. Yeah, let's say dr. So I'm going to say dr here. Now notice that the equivalent, so I could just as well be pulling here, and then I might say dy or something, and then the height changes. But that would be just the same as just, how do I want to phrase this? Because the force that we're going to assume is going to be, well, no, how do I want to phrase this? We basically want to be pulling on this part of the string, and by pulling downwards, all we're doing is just using tension to transmit that pull. And so what we're doing is we're applying a force, perhaps an inward force, rather than pulling. It'd be the same to just push it. An inwards force from some radius to some smaller radius. We could think of it equivalently that way, and it would have the exact same effect. It doesn't matter if you're pushing or pulling. So there's a reason to my madness, and that's because the force that we want to apply is not constant, right? We need it to be just slightly more than the tension force, but the tension force changes. So what we're going to end up doing is we're going to actually have a decreasing magnitude of our force, and we want to be able to, and we can characterize how much force we need to decrease the magnitude, or how much we need to decrease the magnitude of the force by in terms of the radius. So it's a convenient variable to work in. But keep in mind, whether we're pushing on our thing out from the out, pushing it inwards, or just pulling on it via the string, it doesn't matter. It's the exact same phenomenon that's happening. We could probably work out how to do this in terms of the pulling down force. It would just involve a little bit more algebra and might be a little bit more confusing. So I'm going to stick with this for now, but we can talk about it later at the end of lecture if you guys want to. Right, so we have our pulling force, just F. It's not necessarily a constant. It might depend on the radius. In fact, it does. And we know that that the magnitude of that force has to be just ever so slightly larger than the magnitude of the force needed to keep the block going in a circle, right? So we have the formula for that, though. So what I'm going to do is I need more space. This is just m times ac, right? The centripetal acceleration times the mass. That's just from Newton's laws. This is the only force that's present. This force is the tension force plus a little bit more, dr. And we know what that centripetal acceleration is as a function of radius. This is ri to rf. It's m times r omega squared dr, right? So as we can see here, the magnitude of the force is changing with position. Oh, because so that's a fair point. Technically, it should be negative f dr. I should fix that in my notes because that's a good point. The force is pointing in the opposite direction of dl. So dl in this case, it's pointing. It's just pointing. It's just the dr vector in the, say, r hat direction, and f is negative f in the r hat direction. So yeah, you're correct. But yeah, there's a negative sign there because the force is pointing inwards, but I have the sign on the wrong term. But anyway, continuing. So what we get for the work done is it's negative m times Ri to Rf, where, by the way, Ri is, it's in the picture, never mind, it should be clear, omega squared R dr. Now, omega here, keep in mind, is not constant, right? Omega is the angular velocity, and it's speeding up as it goes around, as it's pulled in. So actually, what we have to do is we have to figure out what omega is in terms of R. But this force produces no torque around the hole. As we've made clear, it's a radial force, so it's not going to produce any torque. So so again, just as before, L is conserved, the angular momentum. And so we can use the fact that the angular momentum is conserved to figure out what omega is. So the fact that the angular momentum is conserved means I omega is a constant, right? It means that it doesn't change with time. But I omega is just mr squared. Omega, I is just mr squared, where r is the distance from the hole, the distance the rock is from the hole. And this is equivalently equal to mri squared omega I, right? Because it's the same value for any combination of, or for the appropriate combinations of omega and r, we can say that we can write this value, the angular momentum, in terms of the initial angular momentum. And we know what omega I and Ri are. So we can use this relationship to solve for omega as a function of r. What we get is we get that omega as a function of r is Ri divided by r squared omega sub I. And so we can take that and plug that back in, and that's what we're going to do. So we get that the work done from configuration I to configuration F is negative m integral from Ri to Rf. And then we have to substitute in omega squared. This is Ri divided by r squared omega I, all squared r dr. And so we can do some cheeky factorization. M Ri to the fourth omega I squared, Ri to Rf, and then it's just dr divided by r cubed. All I did was I multiplied this out and then factored out the constant terms, the things that are just the initial values. And so then you can do this integral and you get, it's 1/2 mri squared omega I squared Ri squared over Rf squared minus 1. And that is the work done. Okay, now let's go and let's check using the work energy theorem that this gave us the correct result. A way to, what that does is it'll basically tell us all of our steps were correct. So method 2 for calculating the work just uses the work energy theorem, right? It's just find the difference in kinetic energy, and then that'll give you the work done. So the work energy theorem is just that the work done is 1/2. There's only rotational kinetic energy here. IF omega F squared minus 1/2 II omega I squared. This is the, remember that this is the moment of inertia in the final configuration. This is the angular velocity in the final configuration. And so the moment of inertia is different because the distance the mass is from the center changes, right? And so that affects the moment of inertia. And similarly, the angular velocity also changes. But we already have a formula for omega as a function of r. So what we can do is we can just substitute into this formula, Rf, and that's what we're going to do. So this is 1/2. Well, what's the moment of inertia in the final configuration? Well, it's just m times Rf squared. It's just a point mass some distance from the pivot, times omega F squared, minus 1/2 Ri squared times omega I squared. So far, so good. And now we're going to substitute in omega sub F. So this gives us 1/2 m Rf squared Ri squared Ri over Rf squared omega sub I. Wait a minute, I need to make sure that okay, so that's to the fourth, because it's omega sub f squared, and this is omega sub I squared here, minus 1/2 mRi squared omega sub I squared. So far so good, I hope. And so now we can just factor, or rewrite in factors. So this is 1/2 mRi squared omega I squared, Ri squared over Rf squared minus 1. And now let's just to be on the safe side, let's go and check, and indeed it does check out. So there's actually something that we've kind of done here. We've, at least to an extent, proven, not really proven, but at least checked that the work energy theorem for rotation does work, right? We hadn't actually done that before. That we hadn't checked that it was valid for rotational kinetic energy, but indeed it is, because we get the same answer in these two cases. And further, this kind of indicates that we didn't make any wrong moves anywhere. So those are the two ways that we could have computed the work done. I suppose we could have also used the work energy theorem for translational kinetic energy and just found the translational velocity as a function of, or we could have just written this in terms of translational velocity and all of those things. But the whole takeaway of this whole process is just that in situations that only involve forces that come from a single point, these are those, let me scroll up. These are those central forces. And in our example, it is a central force because the force just comes from the pivot point. You're just pulling down and that pulls it inwards. In those cases, angular momentum is always conserved about that point. So we'll talk about this perhaps later today, but definitely on Friday. But there are other forces that are always radially inwards. These are things like gravity, right? So the fact that gravity always points, is always, like the gravity from the sun is always, the force is always acting towards the sun, it means that angular momentum would be conserved by any process where that's the only force in our solar system, about the sun's axis, of course. So for example, orbits would be an example. So it's a useful point. Angular momentum is conserved in a lot more cases than even translational momentum. Energy is not conserved a whole lot. Usually there's some sort of thermal energy or some sort of external force. Translational momentum is conserved even when energy isn't necessarily conserved, but angular momentum is conserved a lot. It's conserved in most cases, because oftentimes there are no net torques, because things tend to not just start rotating on their own. So because of this feature, because of this fact that that we have this extra formula, effectively it's that the initial angular momentum equals the final angular momentum, that gives us another tool. And indeed, we need that extra tool. And the reason for that is that there are some problems that can only be solved. Okay, maybe that's not true. But let me write this and then I'll add a caveat in a minute. That can only be solved with angular momentum conservation. And that's because they involve external forces. And once you have external forces, this ruins translational momentum conservation. So I say that there's a caveat to this statement, that some problems can only be solved with angular momentum conservation. Of course, that's not true. You can solve a problem however you want, but often, and in general, you can actually solve literally any problem that we've covered in this class using Newton's second law and just analyzing the forces on each individual point mass and doing that. But what we're saying is there are some problems that can only be solved using the sort of conservation type tools that require angular momentum conservation, and you can't just get away with translational momentum conservation. So let me give an example of such a problem. This is the ballistic pendulum. It's another ballistic pendulum, and again, you'll find something similar to this on the homework. Not quite the same. I've added a little bit of a cheeky bit, but there's another. The next type of ballistic pendulum is, let's say, you have your roof, but instead of having just a block at the bottom hanging by a massless string, you just have a chunk of stuff, say a uniform rod of stuff with a center of mass, say, in the middle, and you have your bullet hitting the end. So this is maybe before, and then we have our during picture, have our same rod, but now we have the bullet embedded in it. I don't actually mean to make this longer or to change where the center of mass is, because we're going to treat the bullet not as part of the thing. And now, so at this point, the ballistic pendulum is swinging, and then after it's reached maximum height, say, so this is before it starts moving, but sorry, before it's changed position, but after it started moving. Your ballistic pendulum is, rotated to some degree. Terrible job drawing, I'm sorry. We have our bullet here. Angular velocity at this point is 0 because it's reached the top of its arc, and then it'll fall back down. But the important part is that notice how the center of mass went higher, and notice that the bullet went higher. So this distance, maybe call it h. So then this would be h over 2, since we know the center of mass is in the middle. And so what we note here is that there is an external force that we have to deal with, and that is because this hinge here at the top is providing both a force pulling the object up, which typically wouldn't contribute to the linear or the translational momentum conservation, but this pivot is also providing a force left and right, perhaps. Right, so that does affect the translational momentum conservation, because there would be a force left and right, and so that will affect what the affect the momentum conservation between these two places. However, because we're talking because we know what a useful pivot point is, we can imagine that we're pivoting about this pivot point, and then those forces don't contribute any torque. And because they don't contribute any torque, we can get away with using angular momentum conservation. So first, let's figure out what is the total moment of inertia, say, in this middle case, during and after, I suppose. Well, this is the moment of inertia about one end of the, let's give this a length L. About one end of the rod is 1/3 ml squared, and the moment of inertia of the bullet, a distance L from the axis, is just ml squared. So capital M being the rod, lowercase m being the bullet. So this is just 1/3 m plus m times L squared. By the way, I'm going to go back and double check that the homework problem, which is kind of based off of this problem, is correct. I just realized that I may have left something out, so I'm going to go back and double check on that after lecture, and then I'll confirm. I'll send out an announcement to let you guys know if I'm changing anything. But anyway, right. So that's the moment of inertia here. So let's write down the angular momentum conservation equation. Well, the initial angular momentum, and we're going to do between before and during. The initial angular momentum is just the momentum of the bullet times the distance that the bullet, or the perpendicular distance between the bullet and the pivot. So this is our P, this is our R perpendicular, right? Because the smallest distance that the bullet has between itself and the pivot is just L. So that's the initial angular momentum, and I'm going to assume that this direction is positive, just for the sake of not having a whole bunch of negative signs floating around. So this object would tend to swing around if it were connected to the pivot. So we get a positive sign. And this is equal to the final angular momentum. Well, the final angular momentum can't really be written this way. Instead, we'll just write it in, we'll just use that L equals I omega. We know what the total moment of inertia is. It's 1/3 m plus little m L squared. And we know the angular velocity, or at least we're trying to find the angular velocity omega. And so what we find is that omega is equal to 3 little m divided by m plus 3 little m times v over L, where v is the velocity of the bullet. Okay, so far so good. Put a box around that so you remember to use it later. By the way, this is a typical angular or ballistic pendulum type problem. Maybe you're given the height that it swings up and you want to find the velocity of the bullet or something. Now we can also use energy conservation, right? So what do we know? We know that the pivot is not going to do any rotational work because the pivot is the forces from the pivot point don't do any torque or don't apply any torque because they are located at the pivot point. So what we can do is we can just use the rotation. We can just look at the rotational. We can write everything in terms of rotational kinetic energy. And in the case of the bullet, we can write everything in terms of rotational kinetic energy between these 2 points, because there are no external forces besides the ones that don't do torque, those being the forces from the pivots. So the energy conservation that we get is we get initial 1/2 times the moment of inertia, 1/3 m plus m L squared. Oh, by the way, there definitely is a force that does torque, and that's gravity. But we're going to treat that as an internal force, like we usually do, and so that becomes a potential energy. And then we have I omega. Let me you know what? Let me write this more explicitly. So we have the initial kinetic energy is, say, 1/2 I total. Let's call that initial. It's the initial angular velocity here. The final kinetic energy is 0, right? Because it has no angular velocity. The initial potential energy, let's just call it 0, and then we'll figure out, and the final potential energy will be how much it changed by. So we know that the center of mass went up by h/2 units. So it's capital mg times h/2. And the mass of the bullet went up by h units. So this is mgh. So now we can use our energy conservation that we typically like to use. We get that 1/2 I total omega sub I squared equals 1/2 m plus little m gh. And now I'm just going to substitute in omega sub I and I total. So that is 1/2 times 1/3 m plus little m L squared times 3m over m plus 3 little m squared v over L squared equals 1/2 m plus m gh. Doing some algebra to this, we get that this is m plus 3m divided by 3 times L squared omega squared equals m plus 2 little m gh. want to make sure that that's correct. Yeah, that's correct. And so then we can say solve for the height. How did I get the h over 2? So if the bottom swings up by h units, then the center of mass, which is halfway up, has to swing up proportionally. So it would swing up by h over 2 units. And so this distance between the center of masses is the center of mass raised h over 2 units, and hence we get the h over 2 there. Right, and then we can perhaps solve for h in terms of the initial velocity. This would be 3 times m squared v squared divided by m plus 3m, m plus 2m times g, which is, not a trivial expression, right? Like you could not have got, like, you couldn't have guessed that. You can almost guess the solution for the standard ballistic pendulum, not the extended ballistic pendulum. You can almost guess the solution. This you certainly can't, because it depends on too many things. Importantly, by the way, it doesn't depend on the length of the rod, which is interesting. And you'll find that that's generally true. As long as the rod is uniform, it doesn't really matter what the length is. It only really matters how much it weighs, what its mass is, and the mass of the bullet, of course. Does anyone have questions about this problem? How did I get the initial angular momentum? Right, so remember that the magnitude of the angular momentum is just, one sec, I'll get to that in a minute, Shreyas. So the magnitude of the angular momentum is just p times r times sine theta. And r times sine theta, this is just the perpendicular distance, not pen. It's the perpendicular distance between the object and the pivot. So the idea here is you just draw a line extending your object's velocity and find the smallest distance between the 2 points. That is the perpendicular distance. So all I did was I just simplified this expression using that fact. And so I plugged in P, which is mv, and then the perpendicular L. What if you hit a rod with non-uniform density? Then the moment of inertia changes, right? If this was, and perhaps the center of mass changes as well, the difference in height for the center of mass. Shreyas, so we're not considering the translational kinetic energy because the translational, hold on guys, slow down. So we could have written this in terms of translational kinetic energy, but we have a thing rotating. So we could have written this in terms of the translational kinetic energy of the bullet plus the rotational kinetic energy of the pivot, but the point here is that we have a useful expression for the angular velocity already. We don't really have a useful expression for the velocity of the bullet after it hits the rod. So it makes more sense to just treat everything as treat all of the parts of the kinetic energy that would be translational, just treat those as rotational, because you can. All rotational kinetic energy is just translational kinetic energy of a whole bunch of different parts. Jayon, so you asked, is that a 3 capital M or 3 lowercase m on bottom? Here, this is a 3 lowercase m. How did I get the final potential energy? All I did was I just found the change. I just found how much height the center of mass went up, because we know that the potential energy, the gravitational potential energy, just depends on the center of mass. And then we know how far up the bullet went, so I just added them together. All right, I'm going to continue here. Hopefully that answered your guys' questions. So the whole point of this this exercise is that it kind of shows what things you're allowed to use or what things you can use when you're dealing with collisions that are not necessarily on center. So we can now talk about off-center collisions, which again, there's a homework problem like one of these. So in the example that in this example above, there's an external force, or two external forces from the pivot. There's a force perhaps going up and down and a force going left or right from the pivot. But if we take that pivot away, then we basically just have a collision where the bullet hits a floating rod and there's no external forces. And so that is just a standard collision, but the objects are colliding off-center rather than colliding, rather than having their center of masses collide like we had in the past. Just imagine that this whole thing was in 0G and there wasn't a pivot at the top. Well, then you can imagine that the bullet would hit the rod would move forward a little bit, but the rod would also start to spin, right? And so you'd have to analyze that using angular momentum conservation. But we have the tools for that. Just as a caution here for off-center collisions when you're solving them, the reference point has to be, it has to be in the same place before and after the collision. So you can't like have your reference point track your objects. So I'm just going to take a quick aside. I just need to pull up a video really quick because I have another demo I want to show you. And unfortunately, I can't do this one from home. Because we're going to talk about something called gyroscopic precession, which is a final and very strange consequence of angular momentum conservation. Or perhaps not angular momentum conservation, the impulse momentum theorem, though. It's a consequence of that. Sorry, my internet's being very slow. I'll continue on while it loads. So we're going to talk about gyroscopic precession. And first I need to give some background. Actually, there's a really, anyway. So if the net torque isn't zero, you might ask, is it still possible that the moment of inertia and the angular speed are unchanged? Well, yes, indeed it is actually possible. It is still possible for and I say angular speed, by the way. I mean speed very explicitly, to be unchanged. Which seems kind of strange, right? You might suggest that if the net force is zero, if the net force isn't zero, then how could you have that the translational inertia, which is just mass, and the translational speed, how could those both be unchanged? But of course that's possible. Consider spinning a rock around your head attached to a string, right? There is a net force on the rock. The rock is feeling some inward force. The mass, of course, isn't changing, and the speed isn't changing, but importantly, the direction of the velocity is changing. The reason for this, as I can show you with equations, in this case, torque is dl dt, and this is, of course, a vector equation. And so that implies that dl dt is not zero if omega sub I changes, or sorry, just omega changes direction, right? Because this dl dt just measures the change in your angular momentum. And so if the angular momentum's direction is changing, well, then it's certainly changing. So let me just find a really quick video to show you an example of gyroscopic precession. Oh.
Hi there. If you're watching
Come on.
this video, you're probably already aware of the phenomenon.
I didn't ask for this.
And how you can predict and...
I wanted to show you the Veritasium video because it's excellent, but it's being very slow and not loading. Ah, here we go. So let me just skip to the part where he actually does the demo because, and you guys could watch this on your own time if you really want to. Let me share screen. New share. Here we go.
So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque
so he's doing an explanation. I just want to show you what it looks like, though.
The rotating axis, you could call it R. So torque is of the torque. So the torque is actually down that way, but the torque momentum of this.
So let's just skip to the demo.
The angular momentum of the wheel in the direction of the torque. So I put towards the camera, out towards.
All right, so he's speeding it up.
Now, before I go any further, let's have a
it's hanging from a string.
Setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect.
Oh.
Torque, which is pointing out this way, which is angular momentum in that direction requires that the whole system starts. So that is what the bicycle pushing will spin. All
right, so now, okay, here we go. So he's spinning it up, attached to this string, and then he's just gonna let go.
Oh,
and so, weirdly enough,
as we predicted,
what happens
the angular momentum vector
is that
this way, but torque is pushing it this.
What happens is that it starts to spin. Like the whole system starts to spin, and if the string was more adequately controlled, like I've done this demo in lecture before, if you're just holding on one end, it'll just spin around. I mean, it'll slowly fall, but it will just spin around and not fall immediately, and that's gyroscopic precession. And if you guys have built gyroscopes before, which some of you have, I know it's an engineering project for some of you guys, you'll demonstrate this. So we can now explain that. So let's just draw a picture here. Let me pull up those things. So I'm basically going to draw the picture that, there we go, that he had, but a slightly better setup. So let's say they just have some pivot point, and then you have your wheel. And the other side of your wheel, it's spinning rapidly in this direction. And there is a force downwards, mg, acting from the center of mass, of course. Now, let's think about what direction is the angular momentum in. Well, we know that we can apply the right-hand rule. So assuming that this is spinning, I drew this poorly because I want to have the angular momentum in the other direction. Let's have it like this. There, now it's spinning towards us. So it's spinning, it's hard to draw, but we can apply the right-hand rule. So it's curling towards you. And so the angular momentum is to the right. And the reason why the angular momentum is to the right is because the angular velocity is to the right, again, using the right-hand rule. And they're always in the same direction. Now, we have this force here, and we have this pivot here. By the way, there's one more force at play. That's a normal force pointing upwards. It's not going to do any torque. It's not going to affect anything. But importantly, we can take the cross product of a vector that goes to the right. So R is equal to, say, a distance times, let's give a set of axes, x, y, z. So R is, say, a distance in the I hat direction. It's pointing from the left to the right. The force due to gravity is negative mg in the j hat direction. And so what we can do is, remember back from like the first or second lecture, we know how to take the cross product of two vectors written in terms of unit vectors. Then R cross Fg, which is how you find the torque, that is negative d times mg in the k hat direction. I cross j is k hat, and we have negative dmg. And so what direction does that point in? It points inwards. You may have seen this, this notation before where cross point is, think of like an arrow, like there's feathers on the back of the arrow, and so those would look like an X. So that's inwards. If you just see the tip of the arrow, that's a vector pointing outwards. So the torque is pointing into the board. I'm almost done, so just give me a minute or so. So assuming that all of our deltas that I'm about to write are very small, Newton's second law is the following. It gives us this formula, that delta L, the change in angular momentum, is the torque times a small amount of time that's passed. What this means is that the torque vector points in the same direction as the change in L. The torque vector is parallel to delta L. So if the torque is into the page, that means that LF, which is equal to Li plus delta L, we can figure out what direction LF is in. Delta L is into the page. Li is to the right. And so LF is to the right and into the page. So the picture here is that now L is pointing slightly into the page. And so what that means, using the right-hand rule, if you rotate your hand slightly, it's hard to see. So initially, L was pointing to the right, so you had angular velocity going this way. Now, curling my hand into the page just a little bit, now we have angular velocity this way. So that means that the whole gyroscope has rotated. So now let's say over here. It's hard to draw. Maybe I'll draw another picture. So you had something like this, and now you have this picture. Oh boy. It's not tilted sideways, it's gone around a little bit. So what this torque does, because the torque is always just adding a little bit perpendicular to L, it's just causing it to move a little bit by a little bit, much the same way that the acceleration on a centripetally accelerating object takes its velocity vector and turns it a little bit at a time. So that's what's happening here. I would highly recommend you go take a look at Veritasium's video. It's an excellent video in its full. It was just longer than we had, so I figure that it's better for me to just quickly summarize and you guys can check it out. This whole phenomenon, by the way, this phenomenon where the gyroscope, which is hanging on one end and starts to spin, that's called gyroscopic precession. All right, so let's end it there.